Hello everyone. Today we're going to talk about how to integrate something by a process known as U substitution. So let's get started. We have a lot to get through. Okay, so these are the steps for integrating indefinite integrals using U substitution. So the steps are: first, we want to go ahead and set U equal to part of the integrand. Usually a function inside of a function. That sounds to me like the chain rule with the derivative. So we're looking for a function inside of a function, and we're going to set that equal to a value called u. Then we're going to take the derivative of u, find du dx, and then you're going to solve for dx. Next, you're going to substitute the expression found in step 2 in for dx. Simplify the integral so it is in terms of u. So you want the whole integral to be in terms of u. That's going to be very important. Then you're going to integrate in terms of u. And lastly, you're going to substitute the original value of u back into the equation so the final answer is in terms of the original variable. All right, that seems a little confusing. We're going to definitely take this slow and go step by step through this. So we're going to do several examples. So let's get going. Okay, so let's get going. Our first example here is the integral of the square root of 4x minus 9 dx. All right, so first of all, let's talk about why it is that I have to use this alternate method of U substitution. We know, of course, that I could rewrite this as the integral of 4x minus 9 to the 1/2 dx. Okay, so the integral rules that we've learned so far involve the integral of a power, x to the n. Well, what I want you to understand here is that x has to be a single variable. You can't allow a polynomial, in this case a binomial, to represent x. Okay, so if I am going to follow this rule over here, it has to be that x is a single term, a single variable. In this case, clearly 4x minus 9 is a function in terms of x. It is not a single variable. Therefore, I can't use my normal integration rules. And so because of that, I have to use U substitution. So this is where we have that function inside of a function. You have 4x minus 9 inside of x to the 1/2. So what we're going to do is we're going to go ahead and assign that function inside the function, the 4x minus 9, to be our u. So we're going to go ahead and say u is equal to 4x minus 9. That was step 1. The second step was to take the derivative of this equation with respect to x. So I'd say du is equal to 4 dx. Okay, the next step told us to solve for dx. So we're going to go ahead and divide both sides by 4. And so we would have 1/4 du, or du divided by 4, either one's okay, is equal to dx. Okay, the next step says to substitute the expression you found for dx dx into the equation, or into the integral. So that would be this. We just found that dx was equal to 1/4 du. So I'm going to take my integral and I'm going to replace the dx with what I just found. So I'm going to say the integral of 4x minus 9 to the 1/2, and then instead of dx, I'm going to say 1/4 du. All right, now the next step says make sure that the integral is all in terms of u. Well, clearly I have two different variables here. I have x still here, and I have du here. It's not all in terms of u. Well, I can make that better because I have an expression for u that is in terms of x. In other words, I can substitute that 4x minus 9. I can replace that with a u. So I can say the integral of u to the 1/2, 1/4 du. Which of course we'd want to rewrite. That's all multiplying. It's all in terms of u now, so now we can mess around with it and do whatever we want. So I'm going to rewrite that. I'm going to put my constant out in front. So I'm going to have 1/4 the integral of u to the 1/2 du. All right, so now it's an integral that I can integrate in terms of u. And that's the next step, to go ahead and take the integral of that in terms of u. So I'm going to leave the 1/4 out there. The integral of u to the 1/2 would be u to the 3/2 divided by 3/2, or times 2/3, and then plus c. This is an indefinite integral, so I do need that plus c. Okay, so now we can go ahead and clean that up and finish our last step. So if I clean this up, that would be 2/12, which of course is 1/6 u to the 3/2 plus c. All right, so last step, it said, was to substitute back in my expression in place of u. So I'm going to replace now the u with what I started with, the 4x minus 9. So finally I have 1/6 4x minus 9 to the 3/2 plus c. And that's my final answer. Of course, I could rewrite it instead, saying 1/6 the square root of 4x minus 9 to the 3rd plus c. So those are two different options for how you might see the answer. All right, great job. Let's move on to the second one. Okay, the second problem is the integral of 3 times 3x minus 1 to the 4th dx. Okay, so as we take a look at this, again, we're looking for the function inside the function. So if we talk about inside, what is inside? Well, it looks to me like this 3x minus 1 is what is inside the parentheses. That's what's being raised to the 4th power. That is what we're going to go ahead and set as u. So we're going to say that u is equal to 3x minus 1. Next step is to take the derivative. So du equals 3 dx. Next step is to solve for dx. So 1/3 du, or du over 3, either way, equals dx. Okay, once we have dx by itself, we're ready to go ahead and start the substituting. Okay, I'm going to go ahead and try to do both substitution in the same step. I'm going to substitute the 1/3 du in for dx, and I'm going to substitute my u in for 3x minus 1. So what's that going to look like? It's going to be the integral of 3 u to the 4th, and then in place of the dx is 1/3 du. Okay, so let's simplify this. So obviously my 3 and my 1/3 are going to go away, so I just end up with u to the 4th du. Okay, integrate that. We get u to the 5th divided by 5 plus c. Last step is just to replace the u back in terms of x. So I'm going to put 3x minus 1 to the 5th over 5 and then plus c. And that is my answer. Okay, taking a look at number 3 here. We have the integral of 3x squared times the square root of x to the 3rd minus 2 dx. So again, I'm looking for that inside function. I'm looking for what's inside, either under a radical in this case, or raised a polynomial raised to an exponent. And I can clearly see that here, that is x to the 3rd minus 2. So I'm going to go ahead and set that as my u value. So u is equal to x to the 3rd minus 2. Okay? What would the next step be? Hopefully you're saying you're going to take the derivative of both sides. So du equals 3x squared dx. What are we doing with that? That's right, we're going to solve for dx. So we're going to divide by 3x squared on both sides. So I have du over 3x squared equals dx. All right, next step is to, that's right, substitute that in for dx. And then we're also going to substitute the u in place of x to the 3rd minus 2. All right, so let's get started. We'll have the integral of 3x squared, the square root of, remember x to the 3rd minus 2 is really u. And then instead of dx, we're going to have du over 3x squared. All right, so we're going to clean that up. so that our integral is in terms only of u. And how do we do that? Well, if you look here, you have this 3x squared, and then you have divided by 3x squared. So those are going to cancel. You're noticing a pattern here, hopefully, that this is what happens oftentimes with these u subs, that you should be canceling out everything in terms of x, and now what's left is, I'm going to rewrite it as u to the 1/2 du. Now I can integrate that, and so I get u to the 3/2 divided by 3/2, or times 2/3 plus c. Last step is to go ahead and finish it off. Replace my x cubed minus 2 in for u. So x to the 3rd minus 2 to the 3/2 plus c. And that is my answer. Okay, taking a look at this next one. It looks like a monster, but it's really not that bad. So what I want you to do is go ahead and first of all, decide what your u is. Pause the video. Set your u up, take the derivative of both sides, solve for the dx, and then substitute it in. Then come back to me and let's make sure that you have the right, everything substituted in right, and then we'll finish it from there. Okay, take a look at your work and compare it with mine. You should have set your u value as 1 minus x squared, 1 minus 2x squared, because 1 minus 2x squared was what was inside the parentheses. All right, so then take the derivative. Du is equal to negative 4x dx. Solve for dx. Dx is equal to du divided by negative 4x. All right, now the substituting back into the original. We're replacing dx with du divided by negative 4x, and we're replacing 1 minus 2x squared with u. All right, so that I wrote that as the integral of, I kept negative 4x. I re-put this instead of over 1 minus 2x squared squared. I knew I was replacing this with a u, and I went ahead and changed it to a negative exponent. So I wrote it as u to the negative 2. There are definitely other ways to do that. You're eventually going to want to rewrite it as u to the negative 2. If you didn't do that right here, that's okay. Times, and in place of dx, I put in du over negative 4x. Again, looking for that part that's going to cancel, and it stuck right out to me. Negative 4x's are going to cancel, leaving me with a integral problem all in terms of u. All right, pause the video again, take the integral of that, and finish the problem off. Okay, so let's compare your final steps here. The integral of u to the negative 2 du is u to the negative 1, and then it was divided by negative 1, which of course is the same as times negative 1. And then of course your plus c. All right, so then I know that whatever the u is, which of course is going to be 1 minus 2x squared, is going to get pushed down because of the negative exponent. So I put it right here at the bottom of my fraction. You could have wrapped it in parentheses and put to the first, but you don't need to. And then obviously negative 1 is in my numerator, and again plus c. Okay, as we take a look at this next question, it's asking us the integral of cos squared x sine x dx. So if you're trying to find that inside function, okay, well, it might help to look at this and rewrite it as the integral of cos x quantity squared sine x dx. Now you can see that the inside function is that cosine x. It might also help us to think about when would you have to use the chain rule with differentiation. It's oftentimes with that same inside function that you'd have to use U substitution with integration. So in this case, we're going to go ahead and make our U equal to cosine x. Now go ahead and take the derivative of both sides. Du equals negative sine x dx. Solve for dx. So du over negative sine x equals dx. All right, now it's time to do our substitution. So remember here, we are substituting in the du over negative sine x for dx, and we're substituting a u in place of cosine x. So it's going to be the integral of u squared sine x times, replace dx with du over negative sine x. The idea is to be able to simplify this so everything's in terms of u. So once again, we conveniently see that nice canceling here of the sine x. So we end up here, if I simplify this, with this negative is still here. So I'm going to pull that out front. Okay, it's kind of like a -1. It's a constant that can go out front. Integral of u squared du. And so we have negative u to the third over 3 plus c. Last step is to replace the u with what it's equal to, cos x. So we would say negative of cosine cubed x over 3 plus c. And that is our final answer. Okay, this next question says, which of these functions will u sub work for? And what I want this to drive home the point is that u sub does not always work. And you're going to see what I mean. Remember we said that when we're doing u substitution, there's all this substitution, but at the end, you should be able to come up with an integral that's completely in terms of u. If, when you're doing your u substitution, you're not able to cancel out and have it all in terms of just one variable, namely u, then in fact, u substitution will not work. So what am I talking about? Well, let's take a look at these two different functions and say which one is u substitution going to work for and which one will it not. So with both of them, they both have the same inside function, so both of them we're going to go ahead and say that u is equal to x squared plus 1. Take the derivative and solve for x, or solve for dx. So du over 2x is equal to dx. Okay, so now if I were to now do my substitution, of course that means that I'm going to substitute in the du over 2x for dx and the u in for x squared plus 1. So I would be able to write this as the integral of x times, in place of x squared plus 1, I'm going to replace that with u squared, and then dx gets replaced with du over 2x. So here is the crucial step that allows us to use u substitution. Right now we're mixing up x's and u's, but I am able to cancel this x with this x, and therefore I can rewrite this as an integral all in terms of u. Integral of u squared times du over 2, which I would probably simplify one more step, and this of course is 1/2. That's a constant, so I'd put that out front and I'd say 1/2 the integral of u squared du. So definitely this one works for u substitution, because then I could take the integral of that and substitute, pop back in that x squared plus 1, and I'd be done. Okay, what about letter B? Is this the same? Well, again, we said we have the same inside function, so we're going to go ahead and say u is equal to x squared plus 1, just like we did over here. Du would equal 2x dx. Solve for dx and you get du over 2x equals dx. But now what happens when we take and substitute those same things in? We have the integral of u squared times, in place of dx, I'm putting the du over 2x. And what you notice is that there is no way with this one to cancel out this x. And so we have an integral where we have it in terms of two different variables, u and x. And we cannot integrate that. There is no way. And so this u substitution does not work for this problem. And so we would say that this is not integrable. We could not take the integral of it, at least not algebraically. And so at this point, we would be done with this problem when we say we couldn't integrate it. And so in order for u substitution to work, it's important that you recognize that you're able to cancel the non-u variable, in this case, the x. All right, so I just wanted to take that through with you so you recognize that u substitution is not always going to work. There are times when it will fall short, and this is the example for why that is. Okay, so now we're going to take a look at definite integrals by u substitution. So if we want to evaluate a definite integral and we're using the method of u substitution, how is it different than indefinite integrals? Well, it's the same process, and you'll notice as you copy these steps down that many of them are exactly the same as our first steps for indefinite integration by U substitution. All right, so if I wanted to evaluate definite integrals, what's different? We're still setting the u equal to part of the integrand, usually a function inside a function. We're still finding du and solving for dx. We're still going to substitute the expression found in step 2 for dx and simplify the integral so it's in terms of u like we just talked about. Now we have to worry about those limits, or we call them bounds. So this is the step that is definitely new. We now have to convert the upper and lower bounds or limits in terms of u. So that is crucial. Everything has to be in terms of u. So that is really a big deal. Convert everything, including bounds, to be in terms of u. So that is the huge step that we have to remember. Then we integrate, and then we evaluate the definite integral using the upper and lower bounds from step 5. All right, so let's try a few. Okay, so as we begin this problem, it's the same exact beginning steps. Remember, don't get thrown off by these bounds yet. We're not going to touch them at all to begin the process. The first step is still to identify the function inside the function, which hopefully you could recognize here is this x squared plus 1. That is what we're going to start by setting our u as equal to x squared plus 1. Take the derivative of both sides, solve for dx. So du over 2x equals dx. Okay, now this part we've done this a lot now. We should be able to go ahead and do this pretty smoothly. We're going to go ahead and substitute in for dx and in for x squared plus 1 and make it in terms of u. All right, so what's that going to look like? We're going to have the integral from, and I'm going to actually leave my bounds off right now. I'm going to just do the substitution, okay? So the integral of the x is still there. I'm going to replace the x squared plus 1 with u cubed. And then I'm going to replace my dx with du divided by 2x. Okay? Now, right away, I notice that I can cancel out these x's. So I'm going to go ahead and do that and mark that down. So now I have an integral all in terms of u. All right, so now what was the next step that was listed? That was all about fixing my upper and lower, they called them limits or your bounds. So what do I have to do? I have to replace my bounds. Right now my bounds as they're written are in terms of x. So this original question was in terms of x. Well, my new integral is in terms of u. So right here I have an expression for u in terms of x. I have to change my my bounds, which were in terms of x, into bounds in terms of u. What does that mean? Well, over the side here, instead of having 0 and 1, I'm going to replace those in for x and solve for u. So u is going to equal, let's start with the upper bound, 1 squared plus 1, or 2. That is going to become my new upper bound. My lower bound was 0. I'm going to plug that in and solve for u. So 0 squared plus 1, which is 1. That becomes my new lower bound. Now I have converted my bounds to be in terms of u, and I can go ahead and finish solving this problem as a definite integral. Okay, so I'm going to once again pull this 1/2 out front like I did on an earlier problem. Okay, so then the integral of u cubed would be u to the 4th divided by 4. And of course, this is all now between the bounds of 1 and 2. And so now I'm going to go ahead just and simplify that. So it would be u to the 4th over 8 from 1 to 2. All right, so now I'm ready to go ahead and calculate using my definite integral rules, which of course is to substitute in the upper bound and the lower bound and subtract those. So it would be 2 to the 4th over 8 minus 1 to the 4th, or 1 over 8. So that would be 2 to the 4th over 8 would be 16/8 minus 1/8 would be 15/8. And that is my answer. All right, let's try another one. Okay, let's get started on this next problem. I have the integral from 0 to radical 5 of x all over square root of x squared plus 4 dx. So again, I need to identify my inside function. Hopefully we're recognizing that right away as x squared plus 4. It's the one under the radical. So go ahead and take the derivative of that. So du equals 2x dx. Solve for dx. Du divided by 2x equals dx. All right, so now I'm ready to do my substitution. So this goes in for dx. U goes in for the x squared plus 4. So I'd write this as the integral. Keep off my bounds to start. Okay, so as I write this, I'm going to go ahead and get rid of the fraction and use some negative exponents. So I'm going to have the x, and then instead of writing the square root of u as a bottom, I'm going to go ahead and write it as u to the negative 1/2. Of course, u, because u is equal to x squared plus 4, and then the radical is the 1/2, and because it's in the denominator, the negative 1/2. All right, times dx is going to get replaced with du divided by 2x. So we've seen this a number of times now. Hopefully you're recognizing it. The x's are canceling. Okay, and so now we have it all in terms of u. Before we move on and do the integral, we want to go ahead and change our bounds. So kind of off to the side, okay, we have u is equal to, I'm going to take my upper bound and plug it into this equation. So u is equal to square root of 5 squared would be 5, plus 4 would be 9. So that's my new upper bound. My lower bound would be u is equal to 0 squared, so 0 plus 4, which is, of course, just 4. All right, so let's go ahead and take the integral of this. All right, so again, I have this 1/2 that I'm going to kind of stick out in front. Okay, if I integrate u to the negative 1/2, I would get u to the 1/2, and then divided by 1/2, or the same as times 2. And again, that's between 4 and 9. The half of 2 just kind of goes away, and so u to the 1/2, which of course is the same as square root of u, and I can go ahead and plug in my upper and my lower bound. So it's the square root of 9 minus the square root of 4, which of course is 3 minus 2. So my answer is simply 1. Okay, here's another trig one, and I want to definitely tackle this one as well because this is a little bit different than the other one. Remember we talked about with chain rule with our sine and cosine, our trig functions, when we were doing the chain rule for differentiation. There's 2 different times when we do that. The one time, of course, was if you had something like we talked about earlier where you had cosine of x quantity squared. That would be one time when you would use the chain rule. The other time you'd use the chain rule is if you had something like cosine of an angle that was something other than x, so something like x squared in here. Either of these times were times when you would use the chain rule. So that indicates to us that either of those times, anything like that, would be a time when if you were doing the integral, you would also have to use U substitution. So in this case, if I am doing, if I'm looking at this, what is inside, what is my angle? It is not just simply t. And because of that, that angle, that inside piece, is going to become my u. So I'm going to start by saying u is equal to that inside, the angle, which again is something other than just a single variable. And that is what I'm going to go ahead and take the derivative of. So I would say du equals pi over 12 dt. Obviously t is serving as my x here, so I'm going to solve for dt, which would mean I'd multiply both sides by 12 over pi. So I'd get 12 over pi du equals dt. Oops, dt. All right, so now I'm ready to plug in. Okay, I've got my expression for dt, and I know that instead of pi t over 12, I'm going to put in a u. So I'm going to do the integral, again, leave off the bounds for a second, of cosine of u, and then instead of dt, I'm going to have 12 over pi du. Okay, this is kind of a cool one because there's nothing that needs to cancel. Everything is in terms of u. Okay, so now I'm ready to go ahead and change my bounds and fix them so that they are also in terms of u. So take my equation right here for u and replace the values 4 and 6 in for t, and solve for u. So I'm going to kind of do that down here. So u is equal to pi times 6 over 12, which would of course be just pi over 2. So that's going to be my upper bound, pi over 2. My lower bound would be u is equal to pi times 4 over 12, which would be pi over 3. Okay, so now I'm ready to integrate this. And so I'm going to take this fraction, this constant, 12 over pi is just a constant. I'm going to pull that out front, so 12 over pi. The integral of cos u is, of course, sine u. And then my bounds are pi over 3, pi over 2. All right, so now I'm going to go ahead and evaluate that by plugging in the upper bound and lower bound and subtracting. So I have 12 over pi sine of pi over 2 minus 12 over pi sine of pi over 3. Okay, well, sine of pi over 2, that's sine of 90 degrees, and that's just 1. So this is just 12 over pi minus, this would be 12 over pi times sine of pi over 3, which sine of pi over 3 is radical 3 over 2. And so we're looking at 12 radical 3 divided by 2 pi, or the 2 would cancel into the pi, so I'd have 6 radical 3 over pi. Okay, so my very last step is just to combine the numerators there, and I'd get 12 minus 6 radical 3 all over pi. Okay, so that completes this problem, and that one got a little bit crazy, but that is a good snapshot, I think, of U substitution, first with indefinite integrals, and then here concluding with these definite integrals. So that's it for today. I know this was a lot to take in. I hope you understand this process and that you've done it enough so that it kind of sticks in your brain, and we'll definitely practice it more next time. Thanks a lot. Have a great night.